Hey everybody, Mr. Judson here. So this will be our final week of videos. Our goal this week is to get ourselves ready for that Central Washington final, which again, only the people who are signed up for Central Washington credit will be taking it. I will be sending out an email to you guys either today or tomorrow, basically saying that we need to decide, are we going to take the test at 10 o'clock on Tuesday, or are we going to take it at 6 o'clock in the evening? And really that depends on your parents and when they're available. So you need to have a conversation with them and then be ready to answer that email once that's sent out to you guys. All right, so haven't done an entry task in a while, but I'm just kind of backtracking to our review that we did on Thursday last week over Chapter 4, and trying to kind of tie in what kind of a question would Central Washington ask, and this would be kind of like something they would probably do. It says here that Jack and Jill were walking around a track and decided to have a friendly race. Since Jill is a track star and Jack isn't, she said she would use the outer lane and he could have the inside lane. The outer radius is 56 meters and the inside radius is 36.5 meters. How much farther did Jill run after completing 75 on the curve? So we're not talking about the straightaways. Once they enter the curve, so if you're not familiar with a track, it's sort of an oval shape like this, and we're talking about this part right here where they enter the curve. Okay, there's also another curve down on this end, and we've all seen it. There's multiple lanes. We know the inside lane is shorter than the outside lane, so Jill's obviously going to run a little bit farther, but since she's faster than Jack, I'm confident she'll still take him. We're not really trying to figure out who wins. We're just trying to figure out how much farther did Jill run after completing 75 degrees around this curve. All the way around the curve would be 180 degrees. Okay, so they're not even going halfway around the curve. They've done about 75 degrees of that. Okay, so you guys go ahead and see if you can answer that question. All right, so when you read something like this, probably the first thing you want to think of is, what idea are they talking about? And it sounds like we're talking about arc length. Okay, as we're running around a curve, that sounds like arc length. So for Jill, let's see, 75 degrees out of, normally this would be a full circle, right? So 75 out of 360. The reason we're not doing 180 degrees here, because that's what half the circle is when we say the circumference, which is 2 pi times the radius. So let's see, Jill's radius is 56 meters. See, this is around the entire circle. Now if you want to take the 2 away, then it would be pi times 56. That would be half the circumference. Now we're talking about half of one of these. Then you could do 75 over 180. But I would just treat it as if it's a full circle. It's going to happen anyway. As soon as we do 2 and 360, when we reduce those, we're going to get 1 and 180. That'll take care of for us right there. So I'm just going to grab my calculator. And I'm going to do 75 times 2 times pi times 6, and then divide the whole thing by 360. So 75 times 2 times pi times 56, and then divided by 360. And so what I got was 73.304 meters. That's for Jill. And for Jack, so he's going to do same fraction, 75 out of 360, but his radius isn't as large because he's on the inside lane. So we got 2 pi times 36.5, and then we'll just do the same thing. I've got 75 times 2 times pi times 36.5 divided by 360. And I got 47.778. And so now we just have to subtract the two to see how much farther she ran. So 73.304 minus 47.778. I'm going to go back and just select the values on my screen. So, and what I got was 25.525 meters. You could have stored these two things in memory, but because these calculators, with the updated software, you can just arrow up and select those numbers. That makes it a little bit easier. So even though I wrote down the rounded number, I still use the exact numbers in the calculator. All right, so my good clear answer, Jill ran 25.525 meters farther than Jack. And probably whooped his tail at that. Said a friendly race, but she wanted to win, right? All right, let's try another problem. All right, so we want to be able to simplify each of these expressions. Well, it's been a while since we've done this. Remember, our goal is to always try and get down to one trig function if possible, no fractions if possible, and one term if possible. It doesn't always work, but that's what we're shooting for. Okay? And we had some strategies. Anytime you see exponents of 2, which you see in both of these, it makes me want to think Pythagorean identities. Also, one strategy is if you're not sure what to do, change everything to sines and cosines. Usually that's a helpful thing. Okay, so you guys go ahead and try these two. All right, so if I'm going to simplify this first one, I guess the first thing I'm thinking is this looks like a Pythagorean identity. And I believe that one is a cotangent squared plus 1 equals a cosecant squared. So if I move this 1 over here, it becomes negative, so a cosecant squared minus 1 should equal a cotangent squared. So what I have here is tangent squared of x times a cotangent squared of x. And since those are reciprocals of each other, that should just equal 1. Now if you don't see that, you can go ahead and change the sines and cosines. This would be sine squared of x over cosine squared of x. Cotangent is cosine over sine, so since it's squared, we get cosine squared of x over sine squared of x. And we can see we got the same thing top and bottom, so that's just going to equal 1. These would cancel, and you're left with a bunch of 1s. Alright, so that wasn't too bad. I think the thing that I see first here is there's a cosine squared in both terms. Here's one term, here's the second term. Remember, terms are separated by plus or minus signs. So what I want to do is I want to factor a cosine squared out of each of those, and then I'm left with 1 plus a cotangent squared of x. And we just saw right here, cotangent squared plus 1, that's equal to a cosecant squared. So let's go ahead and put that in. So a cosine squared of x times a cosecant squared of x. And so now I'm thinking, all right, let's change to sines and cosines. So this will become 1 over a sine squared. Which means I've got a cosine squared of x over a sine squared of x. And that's just equal to a cotangent squared of x. So there it is. We have simplified both of those. Let's try another one. Alright, so this time we're asked to verify that this is true, which means I know what the answer is. I just got to show that I can get to it. And so this says 1 over, in the denominator I've got a tangent of x, a cosecant of x, and a sine of x. Somehow I got to show it's equal to a cotangent. You guys go ahead and try it. Alright, so I think what I would do with this one is I would start by calling this first one 1 over a tangent of x times 1 over a cosecant of x times 1 over sine of x. And since these are all reciprocals, I just want to think, okay, what's the reciprocal of a tangent of x? 1 over tangent really equals a cotangent of x. 1 over a cosecant really equals a sine of x. And I would go ahead and call this a cosecant, except if I leave it as 1 over sine of x, well then those two cancel. Right? That sine cancels with that sine. And so now I'm just left with a cotangent of x, and that's what I was looking for. Yeah, so that one wasn't too bad. Alright, let's try another one. Let's see, I believe that was number 3. So, let's see, in chapter 5 here we had to solve equations. It was one of the things we worked on, so let me go ahead and just say, let's give answers from 0 to 2 pi. So let's see if we can go ahead and solve this equation. So when I look at this, I'm thinking the same way I would think as if I had 2x squared minus x minus 1 equals 0. I would start by factoring this. This would have to be 2x times x. This could only be 1 times 1. And if I make that negative and that positive, that'd be a negative 2x plus x. That would give me that middle term. See, I want to start this the same way. I'm going to factor each of these. So I've got 2 sine of x times a sine of x. This could only be 1 times 1. I want that one to be negative and that one to be positive, just like it was over here. See, when I say think this way, my trig function goes where the x is. Okay? Don't confuse this x as being the same as the angle. It's not. This still equals 0, and so, here I would say x equals a negative 1/2 or positive 1. Well, I want to do the same thing here, except this time it's sine of x equals a negative 1/2 or sine of x equals 1. And so now I just have to go to the unit circle and figure out where do those two occur. Okay, sine is negative in the third and fourth quadrant, so let me put those tick marks in. And I want my y-coordinate to look like it's at the halfway point. So that looks like this angle right here. That looks like the halfway point. And this angle. This would be, let's see, 6, 12, 13, 14 pi over 12. Remember, we count by twelfths. This would be 18, 19, 20, 21, 22 pi over 12. So I'm going to say x equals, when I reduce this, 7 pi over 6 and 11 pi over 6. And then where does the sine equal 1? That would be right here. So my other answer would be pi over 2. There it is. I have solved that for all values between 0 and 2 pi. Now if this was missing, I would just say plus 2n pi or n2 pi, however you word that, after each of these. It means, add an additional circle to each of them and you get, do it as many times as you want, you get more answers. You know, it also looks like this is divided up into thirds. You know, if that wasn't there, I believe you could also say x equals pi over 2 plus, see, that'd be 6, 7, 8, any number of 8 pi over 12s, which that reduces down to 2 pi over 3. So let's see, 1, 2, 3, 4, 5, 6, 7, 8. Yep, that hit the next angle. And 1, 2 plus 6, that would also be 8. So yeah, if this wasn't here, this would be a way that you could answer that. All right, let's try another one. All right, so we want to find the exact value of the sine of 285 degrees. And this is important, you guys. When it says find the exact value, in Central Washington we'll do this on a lot of questions. That means you can't just grab your calculator and do sine of 285 and write it down. Okay, that gets no credit on this test. We have to show that we understand something about trig. So, you know, we need to locate this angle on the unit circle and then decide, am I going to do a sum and difference formula? Am I going to do a half angle identity? Am I going to do a double angle identity? I want to make sure I know all of those. Okay, so let's go ahead and give this one a shot. All right, so 285 degrees. I start here, I rotate around, there's 270. That first tick mark, that's 285. And anytime we have to do these, I know we talked about ways you could do it with a half angle. There are some ways you can do that. But I'm usually thinking sum and difference formula. What two angles would I add to get this? And I always want one of those to be 45 degrees. So I'm going to do 240 plus 45. And so then my sum and difference formula for the sine is you take the sine of the first angle, 240, times the cosine of the second, which is 45, plus, and then swap the angles. So I've got sine of 45 and then cosine 240. So let me see if I can find 240 on the unit circle. From 270 I got to back up 30 degrees to right here. And so the coordinates for that would be a negative 1/2 comma negative root 3 over 2. By the way, it's okay to put the unit circle on your little cheat sheet. I think I told you guys you can use a full 8.5 by 11 sheet of paper. I'm really just doing that so you don't have to write little tiny things down. It gives you plenty of space, and you only get to use one side, okay? So you can have the unit circle on there if you'd like. All right, so the sine of 240 is a negative root 3 over 2. Cosine of 45, that's right here. We know those are both root 2 over 2. Plus sine of 45, root 2 over 2. And cosine of 240, that would be a negative 1/2. And so what I get is a negative square root of 6 minus the square root of 2 all over 4. We got a common denominator here. And there it is. There's my exact answer. So sine of 285 is equal to that right there. All right, let's try another one. So this time we're being told that the cosine of theta is equal to 9/5. And what they want us to do is find the exact value for the cosine of theta, the sine of theta, or sine of 2 theta, and the tangent of theta over 2. And let's just say that we are in quadrant number 1. Okay? Again, here we are, exact values. So, you know, I can't use my calculator to somehow do an inverse cosecant, if that even existed, and then figure out the angle and then just plug it in and do calculator work. I can't do that. I need exact values for this problem. You guys go ahead and try it. So I think probably the first thing I would do with this is I would say the sine is the reciprocal of the cosecant. So the sine of theta equals 5/9. And then I would go ahead and set up a triangle. Remember, those reference angles always have to touch the x-axis. It should never be up here. All right? It's always got to be next to the x-axis. So we know sine is opposite over hypotenuse. So now if I do the Pythagorean theorem to figure out what this is, that's going to be the square root of 81 minus 25, which is the square root of, was that 56? And I believe that would simplify down to, see, divide by 2 you get 28, divide by 2 again you get 14. So 2 root 14. I think what Central Washington does is they say find the exact simplified value. So they want us to make sure we simplify square roots as well. All right? So what's the cosine? Well, cosine's adjacent over hypotenuse. So cosine of theta equals 2 root 14 over 9. That does not simplify, so there's my first answer. I know that the sine of 2 theta is equal to 2 sine theta cosine theta. And so that means I've got 2 times the sine, which was 5/9, times the cosine, which was 2 root 14 over 9. And so what I get for that is 10, 20 root 14 over 81. All right, and then the last one I've got tangent of theta over 2, which one of our options for this was 1 minus the cosine theta over sine theta. All right, so let's see, we've got 1 minus the cosine theta, we've got that over here. So that's 2 root 14 over 9 divided by the sine theta, which that's right here. And so what I have is a complex fraction. And so that means I need to multiply everything by the least common denominator, which is 9. So these will cancel, these will cancel. I no longer have a complex fraction. What I have is 9 minus 2 root 14 over 5. There's the exact value for the half angle given this situation. All right. Remember, half angles were not on the front cover of our book. They were on page 410, I believe, is what it was in your book. And so if you're trying to put something down on your note card, that's where you would find those. Double angles, those are all on the front cover of our book. All right, I got one last problem for you. So this problem says that at a coastal city, the high and low tides are the same every day. High tide is at 8 feet and low tide is at a negative 4 feet. And high tide happens every 10 hours. Write a trig equation to model the tides. Okay, you guys go ahead and try that. So if I was doing this, I'd probably just start with a picture to kind of represent what's happening. Here's 8 feet, here's negative 4 feet. That's as low as the tide gets, that's as high as it gets. It doesn't really say that we're starting with high tide or anything like that, but I might as well make the problem as easy as possible. Let's just say we start with high tide and it does this. And so that looks like a cosine curve, right? So I want, I guess I'll do T for tide equals A cosine bx plus c plus a d value. And most of the time when we do problems like this, we're trying to eliminate the C values so that we don't have any horizontal shift. Okay. So let's see, my middle line, we've got from 8 to -4, it's a distance of 12, so that middle line is going to be at 2. And that's my D value, right? So I know that this is going to be +2. That means the amplitude is 6 units above, 6 units below. So I've got 6 cosine of something. And so now I need to figure out the B value. And I know that the period of the graph equals 2 pi divided by the B value. They're telling us right here the period is 10 hours, so I'll plug in a 10, and then we'll just solve for B. So if I bring that B over here to multiply, I've got 10B equals 2 pi. I'll then bring the 10 back over and divide, and so what I get is pi over 5. So pi over 5, and you know the most common mistake that I've seen is there's no variable in here. Well, if there's no variable, this is all just one number and our graph would be a straight line. So we need to have something in there. And the most common thing is just, I'll use little t for time. And so there it is. There's an equation that models the tides for this coastal city. All right, that's what we have for chapter 5. Let me get you guys some practice to work on. All right, so we are now on number C22, page 423. And we'll do 1 to 10, 12, 17 to 23, and 25. All right, so 2 days left. We got Wednesday and Thursday this week to review for our Central Washington final, and then test comes on Tuesday. All right, you guys have a good day. Take care. Stay safe.